Okay, let's go on with our study on multipole expansion. Uh, we have done some preliminary studies earlier. In earlier lecture, we have seen the definition of multipole moments and their behavior as a function of distance from the origin. Clearly, higher multipole moments fall off very rapidly, and higher multipole moments are important very close to the source. So let's look at some more physical interpretation and angular dependency of the multipole structure. So these multipole moments, in concept, they are very similar to the center of mass and moment of inertia in the case of rigid body. They essentially represent the extended particle or extended object, which is a simple particle can be treated as a monopole term. This concept is very useful studying the motion of extended object in such as a rigid body or distribution of charges in the external field. It is also useful to study the or analyze the field produced by an extended object such as a finite mass distribution or finite charge distribution. Now, one of the important point to notice in this case is a multipole moment by definition depends on the coordinate system. So, as a example or as a preliminary, let's go through the Cartesian multipole moments and then we go to the spherical multipole moment or the YLM expansions of the multipole structure. So this is what it makes them somewhat difficult because they may be different based on the origin as well as the coordinate system which you are using. So let's start with the Cartesian dipole moment and we define quadrupole moment. Higher multipole moments can be defined with the higher moments, it's not too difficult. So the dipole moments are essentially very similar to the center of mass of a mass distribution or a point mass distribution. So if you have a charge q1 with respect to some origin placed at r1 and there is another charge q2 which is placed at r2, the multipole moment for these two charges is given by p, which is a vector quantity, is a first charge position multiplied by its charge and the second position multiplied by its charge, which is very similar to the moment of center of mass of the particle. So this can be extended to the arbitrary charge. You can have a finite charge distribution, and by continuity you can also extend it to the continuous charge density distribution. Here density multiplied by the position and integrated over the volume, but the idea is very similar. Like center of mass, it allows us to choose a interesting coordinate system, and this also we can do in the case of multiple dipole moment. Now we see that the conservation also plays an important role in the center of mass, and the similar things can be used also for the uh, dipole moment. Now, in general, dipole moments are vector, and in the Cartesian system, you have a three component px, py, pz, which is essentially given by rho times x prime dv integrated over the given volume. So, you get the full vector definition. So next let's look at the quadrupole moment. Quadrupole moment is essentially generalization or very similar to the moment of inertia for a rigid body. A similar quantity can be defined for charge. However, expression here which we use is a traceless moment of inertia. We could also use a moment of inertia as our quadrupole moment depending on the choice. Some cases they are convenient, and some other case they are not so convenient. The multipole moments are for different charges qi. Mu is the index used for different charges, and the multipole moment is defined like this. This is essentially trace part which is removed from the this thing. So Q is it's essentially superposition of the different charges, multipole moment of different charge, and then we could also as a trace part, or this Qij is essentially traceless part of moment of inertia. In this case also we can extend it to many particle, which we have already done. We could also extend it to continuous system by a replacing summation with the integration over the volume. Let's take some simple example to throw some light on this. So what we have uh, here is a single charge placed at the origin, essentially as a only monopole term. There is no other higher multipole moment, because that is what we see. It's a completely spherically symmetric system. When we have a charge replaced with respect to origin at some point r1, then we begin to see the multipole moment. In this case, the dipole moment of a single charge kept at r1 is given by q times r, and individual components are given here. One can also define the moment of inertia, or the traced quadrupole moment, which is we can see it is just the outer product of the dipole moment given above. So we can also remove the trace and define the conventional traceless multipole moment, and that is also given here. So you can see that when the charge is displaced from the origin, which begin to give all the higher multipole moment. It is nothing to do with the this is physics. It is essentially coordinate system and the way you have defined the multipole moment. So one need to be careful while using a natural coordinate system. One has to adapt to a coordinate system best suited for the problem. Otherwise, it would unnecessarily complicate the matter. Let us look at the potential produced by the single charge displaced. You can see the contour of the bottom and the potential surface on the top portion. As you can see it, it's just media is just meant to show you the at different angle. It is nothing for a charge, single charge, but as distribution gets more complicated, it would begin to show the structure. So let's go ahead with the, let's take a second example, which we call is a standard dipole. The standard dipole essentially is two charges. One is a plus q kept at a distance d by 2 along the y-axis, and minus d by 2, a charge of minus q is kept exactly opposite side on the y-axis. So in this case, there is no monopole term, because total sum of all the charges goes to 0 and they are symmetrically distributed, and so no monopole term. So the dipole moment is simply defined as d, the distance separation between them, times the q. You can clearly see that in this case all the higher Cartesian multipole moments are 0. That is what we call them as a standard dipole. We have seen that in the case of a spherical multipole moment, things are slightly different. Even a pure dipole has a higher multipole moments, but however in this case it is quite simple. So let's look at the potential surfaces. You have one positive and one negative, and lie along the y-axis, and that is what you see is the potential. Let's go to continue with the example. The next example what we have is a quadrupole moment, or the pure quadrupole moment. This can be generated by placing the charge on the corner of the square with the side d. Let's take a charge of minus q placed at d by 2 and d by 2 on the positive quadrant, and then we produce a reflection of that, that is a negative charge placed exactly opposite, and then two more charges to be placed. In this case, the total sum of all charges are 0, and they are symmetrically distributed, so there is no monopole term. You can see that this is like a one dipole flipped around and placed at the same distance, so that makes it the sum of two dipole also to be 0, and there is no total dipole moment. Now we can see uh, the trace dependent or moment of inertia or the trace dependent quadrupole moment for this, which essentially itself is a trace free because of the charge distribution, since the ij I itself doesn't have the trace, so the traceless quadrupole moment is exactly similar to that. We can produce a different charge structure based on this, and then we can conveniently construct the dipole quadrupole moment. Let's look at the potential in this case. It is interesting with the two charges forming an attractive and other two charging a repulsive potential with the saddle-like structure at the origin. Now look at one more example, last example. This we call is a linear quadrupole. It is somewhat given impression that you cannot have a quadrupole with the charge line kept along the straight line. But however, it is possible to construct that. Let's say that you have a charge q at distance d and minus d, the and a negative charge twice that amount at the origin. So if we accumulate all the charges, their sum is 0, so there is no monopole term. Here also the close combination of dipole term goes to 0. You can check this out, it's a trivial computation. On the other hand, quadrupole moment turns out to be diagonal because all the charges are in the straight line. Now you see that the traceless quadrupole moment is also can be constructed based on that. That will have a diagonal component only with the traces 0. Let's look at the potential due to this, and that is what we see is the interesting pattern. Uh, this forms the basis for your various system, that you have a monopole, dipole and quadrupole with respect to Cartesian coordinate system. And if you use some other coordinate system, your multipole structure also would be different. However, this could be very easy to understand this in the Cartesian coordinate system, and their close connection with the moment of inertia and the center of mass makes it even more easier to understand. In the next session, we will look at the spherical multipole moment in the basis of spherical harmonics, which we have done. Essentially, we are looking for a geometrical and physical understanding of the system with the angular dependency to see, because radial dependency we have already seen earlier.